Acids are compounds that we've talked about earlier, and we're going to talk a little bit more about them in this section. Acids are supposed to have the acidic hydrogen listed first, all right? So HCl, hydrochloric acid, HNO3, nitric acid, et cetera, et cetera. Obviously, you saw earlier that acetic acid was not listed with the H first. It was CH3CO2H, and that's acetic acid's weird behavior in chemistry. But ideally, the acids will list the H's that are acidic first. And there are strong acids and there are weak acids. Let's talk about the strong acids because these are the real power horses of chemistry. They're used in lots of reaction. All strong acids are strong electrolytes. So if you have a strong acid, what happens is the H plus, the source of the acid, breaks away from whatever's left, and you've got a whole bunch of H pluses and that remainder happening. So for HCl, the first one, that would be H plus and Cl minus. For nitric acid, that would be H plus and nitrate ions running around. And perchloric acid would be H plus and ClO4 minus. Now, sulfuric acid actually has two acidic hydrogens. So in theory, you would have two H pluses and one sulfate, one SO4 minus 2. And in theory, anyway, this would all be 100%. That's what strong electrolytes do. They break up 100%. Strong acids are strong electrolytes.
Hydrochloric acid is a strong acid. The compound hydrogen chloride ionizes completely, so many ions are free in the solution.
Strong acids, like I said, are very important in chemistry. They do a lot of work.
A water molecule consists of two atoms of hydrogen and one of oxygen. Water molecules are attracted to a hydrogen ion, or proton, to form a conglomeration. There are often 6 and sometimes more water molecules around an ion. Because the hydrogen ion is so small, it is thought to have an average of 4 water molecules associated with it at any time.
The reason acids are important is how the H plus reacts with water. And in the lower right corner there is HCl. It's not really the Cl minus that does anything per se. It's the H plus is how it interacts with water. Now, earlier I said how water has like a slight positive and a slight negative side. And the oxygen side, this part here I'm kind of coloring in, that's where the negative side, if you will, of water is. And it really likes the H pluses, and it makes what chemists call the hydronium ion. Now, the hydronium ion is usually by convention listed as H3O+, which is like a water molecule plus an H+, making hydronium. The video there showed, and that's absolutely right, that there's questions as to really how many water molecules are around H+. There's usually a lot of solvent water relative to the amount of acid H+, so the number isn't exactly always clear. It doesn't really matter though. Just think about the hydronium ion as activated acid, all right? And that's really what makes acids acidic. It's this hydronium ion. It also shows another almost magical power that water has, and it's pretty crazy. And we'll look at this more and stuff as we go through. But all of the acids and stuff, strong acids especially, it's the H plus reacting with water to make the hydronium that makes them so important.
Hydrofluoric acid is a weak acid because it only partially ionizes. At any one moment, most of the HF molecules have not split into their ions.
There aren't that many strong acids, really, and there are literally thousands of weak acids. So a weak acid, you can probably imagine, isn't as strong as a strong acid, and you're right. Weak acids are weak electrolytes, so they don't break up 100% like the strong acids do. Strong acids are strong electrolytes. Every bit of them breaks up, but the weak acids don't. So here's our friend acetic acid again. Acetic acid is a weak electrolyte, and if you remember, like 1 in every 10,000 of those breaks up to the H plus and the acetate. That means that it's a weak electrolyte, and you don't have as much H plus to make that hydronium, that H3O plus we saw on the last screen. So weak acids do not deliver the amount of acid that a strong acid does, and there's a bunch of just a ton of examples of this. So acetic acid, carbonic acid, phosphoric acid, we'll see lots of them. Hydrofluoric acid in the lower right corner is another example of that. So again, weak acids aren't as strong acids. That's because they are weak electrolytes. Not all of the H plus breaks up from the rest of it and stuff, so you don't have as much H plus running around. Bases are the opposite, if you will, of acids, kind of a yin to yang kind of thing. But anyway, a base is just a substance that can deliver hydroxide. Hydroxide is a polyatomic ion. It's OH minus. And if you have OH minus running around, then you have a base. And probably the most important base of all is sodium hydroxide. Sodium hydroxide with that alkali metal sodium ion is a strong electrolyte. It breaks up, it dissolves in water, and it dissociates. It's a strong electrolyte, so it dissociates 100%. So what that means for us right now is that if you put a mole of sodium hydroxide in, you're going to have a mole of sodium ions and a mole of hydroxide ions running around. That's a lot of hydroxide. That's a strong base. So just like acids can be separated into strong acids and weak acids, we're going to see here now that bases can be split into strong bases and weak bases.
NaOH, sodium hydroxide, is a strong base because it dissociates completely. In aqueous solution, it breaks into sodium cations and hydroxide anions.
You can probably see that hydroxide, OH minus, and hydronium, H3O plus, are going to have some interesting reactions going on. We'll talk about that more later. But anyway, for right now, sodium hydroxide is a strong base. Sodium hydroxide dissolves in water. It's got the sodium ion. Anything with sodium for our purposes dissolves in water. It's also a strong electrolyte because sodium just loves to get away basically from hydroxide. And because it's a strong electrolyte, you have a bunch of hydroxides running around. Sodium hydroxide is a very strong base.
On the left is H2O, water. On the right is NH3, ammonia. The dots and lines represent electrons. Ammonia acts as a base in water. It removes a hydrogen ion from water to create hydroxide and ammonium ions. In solutions, only a few hydroxide ions are created at any one time, so ammonia is a weak base.
Ammonia is an important base as well, but ammonia is a weak base. And just like weak acids, 1 in every 10,000 dissociate, weak bases like ammonia also have much less than 100% dissolving and deionizing. So roughly the same number, about 1 in 10,000 ammonia molecules will break up into a hydroxide when it reacts with water and ammonium. And now you can see the relationship between ammonia, NH3, and ammonium, NH4+. Ammonia reacts with water to make ammonium, all right? But it's, again, not very much, like 1 in every 10,000. So ammonia is an example of a weak base, much less than 100% ionized, which means that you don't, like if you put 10 moles of NH3 in, you don't end up with 10 moles of hydroxide. It's much less than that, 1 in 10,000. There are just a few strong bases, but there are literally thousands upon thousands of weak bases out there, and they're all going to be important. But I wanted to show this slide because, first of all, it does introduce weak bases. It also shows how ammonia can be converted to ammonium, or ammonium, you can go back to ammonia. It's a very interesting thing. Also note, ammonia doesn't look like a base. There's no OH minus on it. However, when ammonia reacts with water, hydroxide forms, so keep that in the back of your mind. There are really only a handful of strong acids and strong bases. And the strong acids, I'd really like you to know in Chem 221 through Chem 223, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, and perchloric acid. Those 5 strong acids we're going to use a lot in this class. Likewise, there's really only 3 strong bases that you need to know Chem 221 through Chem 223. Those are lithium hydroxide, sodium hydroxide, and potassium hydroxide. I would recommend memorizing those 5 strong acids and 3 strong bases because they're going to run into a lot. The reason I want you to know those is because, again, there are thousands upon thousands of weak acids and weak bases, and there's no way you could memorize those. However, if the acid is not one of those 5 or the base is not one of those 3, you can assume that it's a weak base. Sulfuric acid has some weirdness about it. You don't have to know that. We're going to talk more about sulfuric acid in Chem 223. Sulfuric acid has some kind of funny things and stuff. We'll talk about that later. So if you want to know it, cool, but it really is optional. I do recommend that you memorize the 5 strong acids and the 3 strong bases, and then everything else by default will be weak. And if you run into one of the other strong ones, like sulfuric acid, or there's a couple other ones, I will help you out with those, definitely. Remember, strong electrolytes are definitely strong acids and strong bases. So all of the weak acids and weak bases are weak electrolytes. And again, there's a whole bunch of them. Notice things like aspirin right there, and also my beloved caffeine, which is not listed. Those are actually weak systems as well, weak electrolytes, and they'll have their own things. And we'll look at all of this a little bit more later. This question states which of the compound below is not an acid in aqueous solution? And that's a really good question. Now, a system that is an acid is supposed to have hydrogen listed first. So even if you don't know anything about the names or anything like that of these compounds, you should absolutely disregard B, D, and E, because hydrogens are usually not listed first in a formula. All right, they're not that exciting. B is phosphoric acid, D is hydrochloric acid, E is hypoiodous acid. So those are all acids, and you can tell them easily because they have the H listed first. Now, A and C both have hydrogens, so they are potentially acids, but as you can probably tell, one of them is not an acid. The first one is our weird acetic acid, and the acetate ion is often listed first, and we're going to see more about why acetic acid is weird, like why it's not listed HCH3CO2, which honestly, as your instructor, I would prefer. But it is listed a lot of times as CH3CO2H, and that's just something we have to deal with. But it is an acid, so we're going to kick that one out. C is ammonia. That's the weak base we talked about. Ammonia doesn't look like a base, but when ammonia reacts with water, it makes ammonium, NH4+, and hydroxide, OH-. So ammonia is a base. The other ones are acid. Ammonia is a base.